Hello students, welcome to the 23rd lecture on particle physics. And in the 22nd lecture, we were discussing about Keon regeneration phenomena. And what I had told you that K0 and K0 bar are the particles which are produced, but when they propagate as the mixture of short-lived and long-lived Keon states, such that you write K0 as 1 by root 2 KL0 plus KS0 and 1 by root 2 KL0 minus KS0 for K0 bar. And this concept of Keon regeneration was given by Gell-Mann and Pais, and they had suggested that K0, which is a strangeness plus 1 particle, may transform into K0 bar, which is a strangeness minus 1 particle. Then we had obtained the expression for the oscillation probability for K0 that remains as K0 after time t, and this was the expression where gamma is inverse of the lifetime of the particle, the short-lived Keon state and the long-lived Keon state. And then what we had discussed is that we have a pion beam, and that pion beam is striking a proton target, and it is giving us a lambda 0 and a K0 through strong interaction process, as lambda 0 has strangeness minus 1 and K0 has strangeness plus 1. Therefore, the total strangeness number is conserved, isotopic spin is conserved, and I3 is conserved. Then we are talking about the produced K0 that propagates as K10 and K20. Then we saw that K10 can decay to 3 pions and K20 can decay to 2 pions. Therefore, the phase space available for K10 is quite less than the phase space available to K20, and therefore K20 is associated with particles which have got short lifetime, while K10 is a long-lived particle. Therefore, we rechristian it by the name KL0 and KS0. And now when KL0 and KS0 propagates, then since KS0 will decay, it has very small lifetime, almost 1 upon 600 that we saw in comparison to KL0, and therefore we are left with KL0. Now recall, this KL0 has again the mixture of K0 and K0 bar, because we wrote K0 as 1 by root 2 KL0 plus KS0 and K0 bar as 1 by root 2 KL0 minus KS0. Therefore, we can rewrite KL0 in terms of K0, K0 bar. Now, if really we have K0 bar, then if we put a target material before this beam, then what was observed is we have a lambda and a pi plus in the final state, or a lambda and a pi 0 in the final state, because we are talking about nuclear target where we have a proton and neutron both as the target materials. And when K0 bar is striking this target, nuclear target, what people have observed a lambda 0 and a pi plus in the final state, or a lambda 0 and a pi 0 in the final state. And these two processes are again strong interaction processes, and that means is interaction cross section is large, strangeness is conserved, isotopic and third component of isotopic are conserved, and this process is not possible via K0, because K0 has a strangeness plus 1 and lambda 0 has a strangeness minus 1. Therefore, this is a minus 1 strangeness, this is a plus 1 strangeness. The change in strangeness is by 2 unit, and this is a forbidden process. Therefore, the important point is we cannot have a lambda 0 and a pi plus through K0. What we will have is a K0 bar interacting with a proton target, and we have a lambda 0 and pi plus in the strong interaction process. Therefore, if you notice that here we have produced a K0 and here we are observing a K0 bar, and that means some of the K0s have got regenerated into K0 bar. And this is what we call by the name Keon regeneration, where to start with, this was a straightness plus 1 particle, this was a straightness minus 1 particle. Therefore, a total of change in straightness is by 2 unit, and this is a rare process, but it has been observed that a few of K0s, they change into K0 bar, and that is why we have these as the final state observables, and this tells us about the Keon regeneration. Now what we are going to do, if we have this KL0 and if we make this target to be thick, why we want to make this target thick is because K0 bar is interacting with these nuclear target materials via strong interaction. Therefore, in all probability, all the K0 bars will be absorbed, and what will be left with is K0. And again, we can have this scenario where K0 is propagating in space, and we have a component of KL0 and KS0. KS0 is going to decay. We will be left with KL0. But now we will place a detector to see that what's the decay mode of this KL0. Now we have seen that in general KL0 decays to 3 pions, which is Cp minus 1 process. While if we find that some of the KL0s are decaying into 2 pi also, that means KL0 is decaying into 3 pion modes, as well as some of the time it is decaying into 2 pion mode. Cp is equal to minus 1 state is for 3 pion. Cp is equal to plus 1 state is for 2 pions, and that means we are talking about Cp violation in the neutral Keon sector. Now that means what we are talking about, a beam of K0 propagates in space as a linear combination of KL0 and KS0, and after a time tau s, KS0 disappears and what we are left with is KL0. Now if this beam traverses a slab of material, the strong interactions will interact differently with K0 and K0 bar. As we have seen that K0 bar interacting with a proton target can give us pion and lambda. K0 bar interacting with a neutron target will also give a different charge state of pion and a lambda. These are strongly interacting particle, while this process is not possible via K0 bar. Therefore, what we are talking about, a K0 bar on proton target giving us a lambda plus pi plus. Now, after emerging from the slab, the amplitude of K0 and K0 bar is say F and F bar. What I am telling you, that some of the K0s are going to get converted into K0 bar. Or if we start with a K0 bar beam, then we can say that some of the K0 bars are getting converted into K0. And we have discussed it on the last turn that the probability of K0 to K0 retention is the same as the retention of K0 bar to K0 bar, or probability of transformation from K0 to K0 bar is the same as the probability of transformation from K0 bar to K0. Therefore, whatever we are talking about K0s as the initial particle, the same is true for K0 bar if that is an initial particle. Therefore, what I am telling you that there is some fraction of K0 bar in the beam of K0 because of Keon regeneration. And then if we are associating amplitudes for K0 with F and K0 bar with F bar, where F bar is much smaller than F, and that is smaller than 1, because the net sum should be equal to 1. Now that is what we are writing it as. The amplitude will be, with a proper normalization factor, Fk0 minus F bar K0, or we can write it and the sum and the difference as 1 by 2 F plus F bar KL plus 1 by 2 F minus F bar KL. Remember, we can write K0 as 1 by root 2 KL0 plus KS0, and similarly for K0 bar. Therefore, we can write these amplitudes KL with the amplitude sum F plus F bar, where F is the amplitude associated with K0 and F bar is the amplitude associated with K0 bar. Now, since F is not equal to F bar, because only a few of them have got converted into K0 bar, sum of Ks has been regenerated when a KL beam traverses a slab of material. Therefore, what we are finding out that we have a K0 and the K1 oscillation is taking place, and then we have K0 bar. And this was first experimentally studied by Christensen, Cronin, Fitch and Turley, who discovered CP violation in 1964, and for which Cronin and Fitch were awarded Nobel Prize. Therefore, this is an important concept where CP violation in the neutral K-on sector was observed by Cronin, Fitch and others, and this is an important concept. And let me again tell you how this CP violation was established, because we were discussing about a K0 beam and then a KL0, and from this KL0, if in the detector we are observing 2 pions besides the 3 pions which is but natural, that means KL0 most of the time that is decaying into 3 pions, but some of the time this guy is also decaying into 2 pions. The important point is that probability is small, but definitely that probability is non-zero, and this implies that there is parity violation in the neutral K-on sector, and this I have shown it with the help of eta. This KL is decaying into pi plus pi minus, and KS is decaying into pi plus pi minus. As we know that KS should decay into pi plus pi minus, but it is not expected from KL. But what has been experimentally found out that this value is 2.284 into 10 power minus 3. This is a non-zero value, and this tells us that there is a finite chance of a KL0 decaying into 2 pi, and this is known as the CP violation in the neutral K-on sector. Therefore, we have talked about K-on regeneration, and then here we are talking about a KL0 giving rise to 2 pions with the fact that most of the time it is giving us 3 pions, but some of the time it is giving also 2 pions. And this tells us that CP gets violated in the neutral K-on sector. Similarly, you can think of this for the K0 beam, where you have a K0 bar beam, and then you have observed K0 in the final state, and there also you can talk about K-on regeneration. Now, similar to K-on regeneration, recently in the B meson sector, which is a beauty sector where the quark combination for the meson consists of either a bottom quark or an anti-bottom, a charm quark or anti-charm quark for the D mesons, and bottom quark and anti-bottom quark for the B mesons. Therefore, we are talking about D mesons and B mesons. D mesons consist of a charm or anti-charm, and B meson consists of a bottom quark or anti-bottom quark. As you can see that D plus has a quark configuration of CD bar, D0 is Cu bar because charge of C charm quark is plus 2 by 3, U bar is minus 2 by 3, therefore in total it is neutral. Therefore the antiparticle of D0 is D0 bar, antiparticle of B0 is B0 bar. Now this CP violation, it was expected that if it really exists, it should also get reflected in the B sector or in the D sector. And in fact, in the B sector, it has been observed. Now, similar to what we had in the case of neutral kaon sector, here also B0 meson oscillation to B0 bar or D0 meson oscillation to D0 bar will happen with the help of 2W boson exchange. And as you can see that you have to, since B0 is made up of B bar D quark and D0 is made up of U C bar quark, therefore what is happening? A B bar which has a charge of, see, if you recall, you have UD as a doublet, you have CS as a doublet, and you have TB as a doublet. This charge is 2 by 3. This charge is minus 1 by 3. This is 2 by 3 minus 1 by 3 plus 2 by 3 minus 1 by 3. Therefore, these are all plus. Now, when we are talking about B bar, that will be plus 1 by 3. When we are talking about, therefore, this charge is plus 1 by 3. Top charge is plus 2 by 3. Anti-top charge will be minus 2 by 3. Again, D bar, D is minus 1 by 3. This is plus 1 by 3. Now here, D is minus 1 by 3. T is plus 2 by 3. And this guy, B, is minus 1 by 3. Therefore, notice that D is emitting a W minus. Therefore, D is carrying a minus 1 by 3 charge. It is emitting a W minus and getting converted into a top quark. Therefore, this minus 1 by 3 is minus 1 is getting emitted. Plus, we have a 2 by 3 charge that will we have at the vortex. We have the charge conservation, as well as we must have the baryon number conservation, which you can see that D and T both are the baryons with baryon quantum number 1 by 3. And then this W minus gets absorbed by B bar and minus 1 charge, and here this is plus 1 by 3. You have a T bar minus 2 by 3. B bar is an anti-baryon with baryon number minus 1 by 3, anti-top with baryon number minus 1 by 3. And then again, similarly with a W plus exchange, it is getting converted into, into a D bar. Therefore, this is absorbing W plus and is getting converted into a D bar. Therefore, this is how we can visualize B0 bar oscillation with the help of 2W exchange, or we can think of D0 to D0 bar oscillation. With the, again, you can notice that we are talking about C bar. Notice C is 2 by 3. This is minus 2 by 3. This is plus 2 by 3. DSB, all of them are carrying charge of minus 1 by 3. This will be plus 1 by 3. Therefore, minus 2 by 3, it is emitting a W minus. It is getting converted into plus 1 by 3. This W minus gets absorbed by the up quark. Therefore, plus 2 by 3 minus 1 will give us either a D or S or B. This is how we think of a D0 or to D0 bar oscillation or B0 to B0 bar oscillation. And as I had told you, in the case of K0 bar oscillation, that delta ML minus delta M, which is MKL minus MKS, this was around 2 into 10 power minus 12 MeV. And this is nothing but 2 into MeV, million electron volt. That means this is 10 power minus 6 electron volt, or this is equal to 2 into 10 power minus 3 milli electron volt, or this is equal to 0.002 roughly. While delta MB, with the present value that is most consistent, is higher than in the case of the mass difference between KL and KS, which was found to be very small. This was this much of milli electron volt, while here this is 0.337 milli electron volt. Now, to summarize, why we are talking so much about CP violation? Because it has got a great physical significance. Now, in a CP symmetric universe, the laws of physics should be the same for the particles as well as their antiparticles. Matter-antimatter symmetry refers to the puzzling abundance of matter over antimatter in the observable universe. We know that we are living in a matter-dominated world where we have electron, proton, neutron in abundant number. But to start with, if we believe in Big Bang theory, which all started with the radiations and then we had equal number of particles and antiparticles, then the question is where those antiparticles have gone. Now, one is there is a parallel world which is made up of antiparticles. The other is because of this CP violation, we can address this problem. And that is why, according to the prevailing theories, the Big Bang should have produced equal amounts of matter and antimatter, yet somehow matter prevailed, forming the basis of stars, galaxies, and life as we know it. We know that all stars, all galaxies, and the life is made up of matter, electron, proton, neutron. Now, understanding this profound disparity, why there is a matter dominance over antimatter in the visible universe, is crucial in unraveling the very fabric of cosmic existence. Now, if CP is an exact symmetry, the laws of nature would be the same for matter and for antimatter. These symmetries are respected by gravitational, electromagnetic, and strong interactions. While weak interactions violate C and P separately, that we have discussed in detail, CP is still preserved in most weak interaction processes. We have also discussed the processes where weak interactions are where in weak interactions CP is conserved, but the quest to comprehend matter-antimatter asymmetry and CP violation spans across various fields of research, from high-energy particle physics to cosmology. We have seen that CP violation effects have been observed in neutral Keon sector as well as what I am telling you in the B sector. And the effect of CP violation in the B sector is larger than what has been observed in the neutral Keon sector. Now, the evidence for CP violation in the decay amplitude at a level higher than 3 standard deviation, while 5 standard deviation is said to be a discovery. That means we firmly believe on an observation which is at 5 sigma or more than that. Below that, we cannot guarantee it with 100% surety, and that is why presently the results are available at 3 sigma, and people have talked about CP violation in neutral D as well as the strange baryons B quark sector. These assess CP symmetry, or you can say that CP symmetry is violated in certain rare process as discovered in neutral Keon decays in 1964 and observed in recent years in B decays. But the scale of CP violation in the quark sector, because we are talking about Keon, US bar, U bar S, etc. Then we have neutral kaons, which are made up of K0 and K0 bar, and that is DS bar or D bar S. Similarly, we are talking about CU bar or U bar C. D0, B0, B0 bar is B bar D or DB bar, etc. Therefore, in recent B decays it has been observed, and then we are talking about some results in the D meson sector, neutral D meson sector, but the scale of CP violation in the quark sector is very small and cannot explain this matter-antimatter asymmetry which presently that exists in nature. Now, a dynamically generated matter-antimatter asymmetry of the universe requires additional sources of CP violation, and such sources are naturally generated by extensions to the standard model of particle physics. That is what we talk about beyond the standard model. Therefore, there are models which talk about CP violation at a larger scale, but they go beyond the standard model. While present results, experimental results that we have, they are consistent with the standard model of particle physics. Now we shall stop at this point, and before leaving out from this lecture, let me tell you that besides the quark sector, there is a very important sector that is known as the lepton sector, where people believe that CP violation in the lepton sector will give more information. And for this, neutrino experiments are going on as well as they are planned with, which shall be discussed in unit dealing with neutrinos. Therefore, it is expected that we will get more information regarding CP violation in the neutrino sector, which is a leptonic sector, and that is the place where the chances are, or people have got expectations that there will be more information regarding this CP violation in the leptonic sector, and that may help out to understand matter-antimatter asymmetry in the present universe. Thank you very much, and in the next lecture we are going to talk about time reversal operation.